Hello everyone. So this is a question from JEE Advanced 2026 paper 1. The 2s and the 2p orbital energies of hydrogen atom are E2s and E2p respectively. The 2s and the 2p orbital energies of lithium atom are E2s and E2p respectively. Okay. The correct options about the orbital energies are, okay, so few options are given to us. So the chapters involved is structure of atom and periodic properties. Okay. So for this question, we have to know the energy level diagram for H atom and multi-electron atom. Okay. Energy level diagram for H and multi-electron atoms. Okay. So energy level diagrams, they represent the arrangement of orbitals in order of their increasing energy. Okay. Represent arrangement of orbitals in order of increasing energy. Okay, so with respect to diagram, um, so this is how it looks like. Okay, so this is for A is for the hydrogen atom and B is for multi electron atoms. Okay, a very important point is that energy of different orbitals of H and H like particles or species depend only on n, or the principal quantum number. Very important. Energy of different orbitals of H and H like species depend only on n. Okay, so in this diagram you can see, for example, 2s and 2p have the same energy because their principal quantum number is 2. 3s, 3p, 3d has the same energy because their principal quantum number is 3. Okay, but for multi-electron atom it depends on n as well as l. For multi-electron atom, energy depends on n as well as l. Okay, n is the principal quantum number, l is the azimuthal quantum number. Okay, so with respect to the diagram you can see, for multi-electron 2s and 2p have different energy, 3s, 3p, 3d has different energies. Okay, so I can say that for multi-electron atom energy depends on n as well as l, or I can say it is directly proportional to n plus l. Okay, which is famously known as the n plus l rule. Okay, in option A we have to compare E2p of lithium and E2s of lithium. Okay, so we can use the n plus l rule here. For 2p, n plus l will be equal to 2 plus 1, which is equal to 3, and for 2s, n plus l will be equal to 2 plus 0, which is equal to 2. Okay, so therefore I can say that energy of 2p of lithium is more than energy of 2s of lithium. Okay, in the diagram also you can see, for multi-electron atoms 2p has more energy than 2s. Okay, so therefore option A is correct. In option B we have to compare E2s of hydrogen and E2p of hydrogen. Okay, so for uni-electron species we know that energy depends only on n, which is the principal quantum number, and 2s and 2p both have n is equal to 2. So therefore E2s of hydrogen is equal to E2p of hydrogen. And with respect to diagram you can see, for hydrogen 2s and 2p have the same energy. Okay, so therefore option B is correct. Okay, in option C we have to compare E2p of H and E2s of lithium. Okay. For H, we know, or H like particles, En is equal to minus 13.6 into Z square by N square electron volt per atom. Okay. Now, for lithium and other multi-electron atoms, we have a formula which is a rough approximation. For lithium and other multi-electron atoms, E is equal to minus 13.6 into Z effective whole square divided by N square electron volt per atom. Okay, where this Z effective is the effective nuclear charge and it is equal to, so I can write Z effective is equal to Z minus sigma. So this Z is the atomic number and sigma is the shielding constant. So this is our shielding constant and it is calculated using Slater's rules. Okay, calculated using Slater's rules. And we have different formulas for H and Li, or you can say for multi-electron atoms. Okay, because in H atom, only force of interaction is the attractive force between the electron and the positive nucleus. So this is what is going on in the H atom. But in multi-electron atom, for example, let's say the lithium atom. Okay, in addition to the attractive force between electron and nucleus, so there is attractive force between the electron and the nucleus. There are repulsive forces among the electrons. So this guy will be repelling this guy. Similarly, this guy repels this guy. Okay, and the attractive force on the outer shell electron are greatly reduced by the presence of the inner shell electrons, because they produce something known as a screening effect or a shielding effect, okay, between the outer shell electron and the nucleus. Okay, so therefore the net positive charge experienced by the electron, by the outer electron, is much less. Okay, and that is our Z effective. Okay, and Z effective depends on the actual nuclear charge, that is Z effective is equal to Z minus sigma. Okay, and because of this particular reason, orbitals of different atoms don't have same energy. Okay, so we have to compare energy of 2p of H and energy of 2s of lithium. Okay, energy of 2p of H I can write as minus 13.6 divided by n will be equal to 2, so 2 square is 4 into 1 square electron volt per atom, and energy of 2s of lithium will be minus 13.6 into Z effective whole square divided by n equal to 2. So n square is 4. Okay. So in the case of lithium, we know that its configuration is 1s2, 2s1. Okay. So this is our n shell and this is our n minus 1 shell. Okay. So all the electrons in n minus 1 shell, that is these two electrons, shield the outer electron to an extent of 0.85. Okay, which is according to Slater's rules. So therefore the screening constant will be equal to 0.85 into 2. Okay, so there are two electrons and each of them shield to an extent of 0.85. So therefore the shielding constant is 0.85 into 2. So therefore sigma is 1.7. Okay, so therefore the Z effective will be equal to 3, which is the atomic number of lithium, minus 1.7, which is equal to 1.3. Okay, so instead of Z effective, I can write 1.3 whole square. So you can see this is a more negative value. Okay, so therefore energy of 2p of H is greater than energy of 2s of lithium. Okay, so therefore option C is incorrect, because option C says that energy of 2p of H is less than energy of 2s of lithium, which is incorrect. Okay. Now coming to option D. In option D, we have to compare energy of 2s of H and energy of 2s of lithium. Okay. So energy of 2s of H will be minus 13.6 into 1 square by 4 electron volt per atom. Energy of 2s of lithium will be minus 13.6 divided by 4 into Z effective whole square, and this Z effective we have calculated as 1.3 square. So this whole value is more negative compared to this value. So therefore energy of 2s of H is greater than energy of 2s of lithium. So therefore option D is correct. Okay. So therefore the correct answer is, so A is correct, B is also correct, and D is also correct. Okay. Thank you.